Hello friends, I am Bindu Trikha, Assistant Professor IMS Ghaziabad. Today we will be discussing about JK flip-flop. In this flip-flop, we have designed so as to overcome the limitations that we came across in SR flip-flop. With SR flip-flop, as we have seen that when both the inputs are 1, the clock is high, the output is invalid. That means we cannot predict the output when S and R both are 1. Now, to overcome this particular limitation of SR flip-flop, a JK flip-flop was designed, and let us see how a JK flip-flop was designed. The S input is converted to J input, the R input is converted to K input, and the output from output Q is given as a feedback to the NAND gate with the input k with k as the input, and the output q bar is given as the input to the NAND gate with the input as j as the input. This is how a JK flip-flop is designed. Now let us see its working. In JK flip-flop, we are considering NAND gates, and we have made a truth table for NAND gate as well, so as to uh, easily interpret how a JK flip-flop works. This NAND gate we have already discussed that when both the inputs are 1, the output is 0, otherwise the output is 1 in all other cases. Now when clock is low, the input has no effect. That means this flip-flop is not working at all, and it works only as a memory element. That means there is no change in the output. Whatever previous output we have, they would remain as it is. Now, let us consider case 2 when the clock is high, and say let us assume j is 1 and k is 0. The clock is high, j is 1, k is 0. And let us assume that the previous output q was 0, so and q bar was 1. These are the previous outputs, because in flip-flops the previous outputs play a very important role in determining the current output. Now this 0 would be going as an input to gate G2, and 1 would be 1 from Q bar would be going as an input to NAND gate G1. Now, let us see the truth table for NAND gate. When all the inputs are 1, the output is 0. So, the output for G1 is 0, and when even one of the inputs is 0, the output becomes 1. Thus, the output from G2 is 1. Now, this highlighted portion, as you can see, is a SR latch with NAND gate. SR latch with NAND gate means when one of the inputs of NAND gate is 0, the output is 1. That we know. So, we have output from G3 as 1, and this one would be going as an input for G4. Now, G4 has two inputs. Both the inputs are 1. The output would be 0. Thus, we can see the current output for the case j is equals to 1, k is equals to 0, and when the previous output was 0 and q was 0 and q bar was 1, the result is now q is 1 and q bar is 0. Now again the same thing, j is 1 and k is 0. We would consider what happens if previous output was reversed. That is q was 1 and q bar is 0. Here let us see, have a look that we have not changed the value of j and the value of k. Only the previous outputs have been changed. This is because we can have any of the possibilities. Q can be 0 or Q can be 1 in the previous output state. Now this one from previous output Q goes as an input to the NAND gate G2, and the 0 from Q bar would be going as an input to the NAND gate G1. Now since both the NAND gates G1 and G2 have 0 as the inputs, the output from both the gates would be 1. And let us now see the previous output. This again works as an SR latch with NAND gate. Here the output from G4, the previous output from G4 would be going to the G3 NAND gate, and it is 0. And thus the G3 would be having 1 and 0 as the input. So the output from G3 would be 1, and this one is now going to G4, and thus we get 0 as the output from G4. So we are having the current outputs as Q equals to 1 and Q bar equals to 0. Thus in both the cases, whether Q was 1 or Q was 0, the current output is Q is equals to 1 and Q bar is equals to 0. That is a set state. That is a set state. So when clock is high, J is 1, K is 0, Q is equals to 1 and Q bar is equals to 0. This is the final output, current output. Now let us consider case 3 when clock is high, J is 0 and K is 1. This is the scenario. Now let us have Q as previous output Q as 0 and Q bar as 1. The previous output has been marked by red alphabets, and the current is marked by the purple alphabets here. Q is equals to 0 and Q1 is equals to Q bar is equals to 1. Now the inputs for G2 NAND gate would be 1 1 0, and for G1 NAND gate it would be 1 1 0. That means in both the cases for G1 and G2 the output would be 1. And now again it behaves as an SR latch with NAND gate. Now here the output from Q, previous output from Q0 moves as an input for G4 NAND gate. G4 NAND gate has two inputs 0 and 1, thus resulting in a output of 1, that is Q bar. So current Q bar would be 1. This one would be going as an input to G3 gate. Now G3 NAND gate has two inputs 1 and 1, thus the output becomes 0. So we would be having the current outputs as Q is equals to 0 and Q bar is equals to 1. Now let us reverse the case. Let Q be 1 and Q bar be 0. Previous outputs be reversed. Now according to these previous outputs, G2 would be 1 1 1. Input for G2 would be 1 1 1, and for input for G1 would be 0 0 1. Thus the output from G1 would be 1 according to our NAND gate truth table, and the output from G2 NAND gate would be 0 based on the truth table for NAND gate. Now this again behaves as an SR latch with NAND gate, and we know that when one of the inputs for a NAND gate is 0, the output would be 1, and when this one would go as an input for G3, it would become 0. So Q is 0 and Q bar is 1. Thus we can say when clock is high, J is 0, K is 1, Q is 0 and Q bar is 1. These are the current outputs. Now let us see case 4. In this case, we have assumed that J is 0 and K is 0. Now since J is 0, K is 0, and let us assume that the previous outputs Q is 0 and Q bar is 1. Thus the input for G2 would be 1 0 0 and G1 would be 1 0 1. In both the two NAND gates, G1 as well as G2, the output would be 1. Now this is a SR latch with NAND gate, and the output 0 would be going as an input for G4 NAND gate, giving it as the output generated so far is 1, and 1 would be going as an input to G3 NAND gate, and 1 and 1 would make it as 0. So Q would be 0 and Q bar would be 1. Now, let us assume that the previous output Q is 1 and Q bar is 0. This Q, the input for G2 gate would be 1, 1, 0, and the input for G1 gate would be 0, 0, 1, thus leading to the output from G1 and G2 as 1. Now this SR latch with NAND gate, for this SR latch with NAND gate, G3 would be having two inputs 1 and 0, thus leading to an output of 1, and G4 would be having two inputs 1 and 1, leading to the output 0. So Q would be 1 and Q bar would be 0. Thus we have seen that when J is 0 and K is 0, the output is not changed. Whatever output we were getting in the previous states, the same output is received as the current state or next state, we can say. So when clock is 1, J is 0, K is 0, there is no change in state. Now let us come to case 5. Here again we have clock is high. Now J is 1 and K is 1. As you can see from this particular figure, we have entered the values as well. And let us assume the previous output Q as 0 and Q bar as 1. This 0 would be going as an input to G2 gate, leading to the three inputs of G2 gate as 1 1 0, and the three inputs for G1 gate would be 1 1 1. Now the output from G1 would be 0 and G2 would be 1. This is a SR latch with NAND gate. Now here, if any of the inputs for NAND gate is 0, the output is 1, that we know. So the output from G3 gate would be 1, and this one would now be going to the G4 gate as input. So G4 would be having two inputs 1 and 1, leading to the output Q bar as 0. So in this case, we would be having Q as 1 and Q bar as 0. That means a toggling has occurred. We have seen the toggling has occurred. Previous output was 0 and the current output was 1. That is, previous value of Q is 0 and now the current value of Q is 1. Let us see if this happens in the next state as well. That is, when Q is 1 and Q bar is 0. Now G2 input for G2 would be 1 1 1 and the input for G1 would be 1 1 0, thus leading to output from G1 as 1 and output from G2 as 0. Now this SR latch with NAND gate has uh, two NAND gates G3 and G4. The output from G4 would be 1, because if any of the inputs for a NAND gate is 0, the output is 1. We know this. And when this one goes as an input to G3 NAND gate, the inputs for G3 would be 1 and 1, leading to the output for Q as 0. So we can see that Q is 0 and Q bar is 1. Now here we can see again that the toggling has occurred. Q is 1 and Q is 1 for the previous state, and for the current state Q is 0. So we can conclude that when clock is 1, J is 1 and k is 1, the state is toggled. This is the characteristic table for JK flip-flop. Here we can see that when clock is 0, whatever previous input is, whatever value of j and k is, the um, output remains the same. That means the qt and qt plus 1 are the same. That means it works as a memory element. When clock is high, j is 0, k is 0. Again, the jk flip-flop works as a memory element. There is no change in the output. When clock is high, j is 0, k is 1. Uh, the outputs in both the cases, whether qt is 0 or qt is 1, the qt value of qt plus 1 is 0, that is a reset state. And when j is 1 and k is 0, clock is high, the output is set. That is, whatever previous output was, the current output is value of q is 1. That is a set state. And in the last case, we can see when clock is 1, j is 1, k is 1, the state is toggled. That is, if the value of q was 0, the current value of q is 1, and if the previous value of q was 1, the current value of q is 0. And this is all about JK flip-flop.